material. That material is not from my book, but from my survey paper, the book Jens edited. Okay, so it's not really the science book. Okay, so can I start?
Yeah, so problem sessions are going to be here, right? I mean, that's the big
Yeah. So can I start? Okay. So my second lecture is concerned with L and M-convex functions. These are notions centered in discrete convex analysis. Okay. So today, properties of two kinds of discrete convex functions called L-convex and M-convex. So L stands for lattice, as you will see from the definition later, and M stands for matroid. Okay. And before giving the definition, I will give you the picture that shows the class of discrete convex functions I'm going to define. So f is a function on Z. Okay. So yesterday we considered univariate function, but today we have n variables, and values is real, extended to infinity. And this is the entire class. And among them, there are some class called convex extensible. So convex extension is possible. The definition of this term is that the function on discrete point is convex extensible if there exists some function which is convex in ordinary sense, such that fx equal to f bar x for any integer point. So this is a natural definition of convex extensibility. So yesterday we had a zigzag line which was not convex extensible. And now important classes are M and L convex functions. Actually here around here L convex. I'm going to define here M convex arising from matroid. But I also define some variants which is larger than that, called M natural. Strange name, sorry for that. Okay, L natural is L natural. And also it's larger. So we're actually M and M natural are equivalent notions, but they have containment. And we have some interaction here. The interaction here is, it turned out that this is a separable convex function. That means that fx in n variables actually split into the sum of univariate functions, convex functions. So these phi is the univariate function, but convex in that sense. So this is the object that we have considered yesterday. So the intersection of these two is exactly the same as this. This is a small theorem. now I'm going to define what are they, the yellow part. Okay. Now I consider L-convex function as well as L-natural convex function. So the definition is this. Actually, there are a number of equivalent definitions. But let me start with the definition of L-convex here. And I have a convention for notation. For function here, L and L natural, I write G for function and variable is P. And here is a notation F of X. The reason is that actually these two objects are conjugate to each other. So maybe you could think of P as a potential. It's a correct understanding, potential. And X is for flow. Yeah, so that's why I distinguish these two notations. And so now I have a function G defined on integer point and taking values, possibly infinity. And definition is that G is L-convex. If and only if two conditions are satisfied. The first is submodularity. This is a familiar inequality to you. Okay, if you have in 2 dimensions, P1 and P2, you consider 2 points, say P and Q, and you look at the maximum. This is denoted like this. This is a vector of component-wise maximum vector. So each component is a maximum of these 2. And this is minimum. Oh, good. Okay. So submodularity on integer lattice means that this is greater than or equal to this. This is usual submodularity. And there's another condition that this function G should behave linearly in uniform increase of variable P. So that means that there exists some number R, and for any point P, if you increase the argument by uniformly, so this is a vector of 1, 1, 1, 1, 1, 1, then it is equal to the original value plus R. The point here is R is universal, independent of P. Okay? And oftentimes, this is equal to 0 in applications. Often, this is a definition, but in applications, often R equal to 0. So that means this function is invariant in this direction. Okay? So this is a definition, but can you imagine any function satisfying this? Actually, you are familiar with this type of function already. Well, I'm not yet skilled enough. Sorry? Oh, no, really, the function value is real here. So, but in combinatorial optimization, often R is 0 or maybe integer, because you could think of 2 versions. So, for example, the canonical, in a sense, canonical example is n equals 2. Okay, so G has 2 arguments. Now consider such a function phi. Phi is a univariate concave convex function. So phi looks like this, the familiar object. And then this is, the claim is that this is L-convex function. Why is the case? The second condition is easy to verify. If we increase P1 and P2 by 1, they cancel. So we have P vector P plus 1 is G P. So we have R equals 0. Now the submodularity. So this should be obvious to experts in combinatorial optimization, but let me try to explain it. Okay, why this is submodular? So to prove submodularity, we consider 2 points, P and Q. If one of these is dominated, then submodular inequality is trivial. So we only have to consider such case. Okay, and this is, so this is a picture we have to work on. Now, we introduce a notation delta P is P1 minus P2, just to simplify notation, this part. Okay, and naturally, delta Q is Q1 minus Q2. So G of P is in this notation, phi delta P. G of Q is phi delta Q. Now, what is delta PQ and delta P intersection Q, mean Q? And the crucial observation actually is simple, is that there exists some number. So you draw this picture. Here we are concerned with the difference of coordinates, so we draw such a picture and project on it. And you consider some axis here. Then this coordinate is delta P, this is coordinate delta Q, along this line. Okay? Along this line. Then it goes here. Oh, it's a poor picture. I will change. I should have done better. I should have done better. Well. Here we project on this line. This is line of this. The sum is constant. So here we have this. Okay, and this is delta Q, and this is delta. So from this picture, it's obvious that there exists some, so that this is a convex combination of these two, and with the same ratio, but reversed, we have this. So there exists some lambda such that this is 2. For some lambda between 0 and 1. Now, let's compute the value of this function G, P, union, or join. Then this is this, lambda or something. This is lambda or something, 1 minus lambda delta Q, because of the definition of this. And since this is convex in one variable, then you can say that this is lambda here. This is by convexity. And this is, by definition, this is GP, lambda GP, 1 minus lambda GQ. And write a similar formula for this just by changing this, then this automatically 1 minus lambda. Now, same with using the same inequality, but now with different coefficient, we have this. Okay. So by adding these two, we obtain, so add these two to obtain submodular inequality. So this is a simple proof, but it's important. Now, as a corollary, we can derive a famous, well-known function by adding these inequalities. So if you look at the definition here, L-convex function is closed under addition. If G1 and G2 are L-convex, then the sum G1 plus G2 is also L-convex because of this. So suppose we have a graph like this. For each I and j, suppose we have a function phi j of univariate convex function. Then we can define function p where pi is associated with this. So p is a function as a vector associated with vertices. And we can define the function by using this as sum of phi j, pi minus pj, where ij is an edge. So we have this. And this is the typical function that arises in network flow, the minimum tension problem. Or if you are working in image analysis, this is called energy function, the second part of the energy function. You can add the first, but here I use this part only. So this is an important function in combinatorial optimization. And since we know that each term is L-convex, and sum of L-convex functions is also L-convex, we can see that this is L-convex function. Okay? So this is a canonical example of L-convex function. Okay? Any questions? Okay. Now, in the picture, I had L natural. What is that? Now, I'm explaining that. Now the problem. So today I don't mind. Okay, so L-convex function is linear in a particular direction. So definition here was GP, GQ. This is a submodular function, but has a special linearity for in the direction, special direction, okay, for any point g p plus 1 is linear here. So often R is 0. Since this is linear in spatial direction, actually one dimension is redundant. Okay, if you have this picture, okay, and if you know that function vary on this, maybe it's better to write this way. Suppose we have 3 coordinates, and the function varies linear in this 1, 1, 1 direction. We can just concentrate on this coordinate plane. So this is what I'm going. So G is, now suppose G tilde is L-convex in variable P naught, P1 to Pn. Okay, so suppose we have L-convex function in n plus 1 variable. Then we define function g by fixing, say, just one coordinate, say 0. Okay, so it's derived from L-convex function by fixing one coordinate. Then definition, I call this L natural convex function. Okay, so L natural convex is by definition is a restriction of L convex function to a hyperplane. And since we know that example, the function g is L-convex. And now suppose we fix P2 to be 0. What we get is the original, that univariate convex function. So the univariate convex function is particular case of L natural convex function. Okay? And by adding the separable convex function is L natural convex function. Okay? Because each of them is L natural, and L natural closed because of this. Okay. But there is a number of characterizations of L natural convex functions. So this was original definition. Okay. So definition 1. Or maybe I shouldn't say many definitions. I would say characterization or theorem. Or maybe it's not real theorem, but characterization, so I would say proposition. So now given function in n variables, this is L natural convex if in this sense, if and only if we define the function g tilde from this by the following formula. Okay, here, so suppose we are given g, and we are going to define g tilde having one more variable by this expression. P is a vector, P naught is a scalar. Okay, so this is n dimension, this is 1 dimension. And this 1 is the same as before, 1, 1, 1, but n dimension. And G is L natural convex if and only if this function is L convex. It's easy to see from this. Okay. So in a sense, L and L natural are equivalent. If we have one, we can construct the other in a simple way. But it turns out that, so here I talk about n and n plus 1 variables. But what if we have fixed number of variables n? Then L in n variable is n natural in n variables. We can prove this. Okay? And in a sense, this is the same as L in n plus 1 because of this correspondence. Okay? So there are other characterizations of L natural convexity. So here I focused on submodularity. Actually, we don't see any convexity yet. It's not.
You have claimed there is a convex expansion.
I didn't claim yet.
Well, you drew it. It was in the picture.
Where?
That
Not yet here. Did I?
that every L.
Oh, at the beginning.
Yes.
You're right. But I didn't prove it yet. I announced it. Okay, it's still them. I'm trying to prove it later. Okay. Okay, good. So logically, I didn't say anything about convexity yet. And I'm going to enumerate the characterization of L natural convexity. So the first one is this. So G is L natural convex. And this is the same as this. So let's assume that these are equivalent. And in this definition, I always refer to functions in n plus 1 variables, okay, when defining the L natural convexity in n variable function. So it's not really good. We don't want to expand the space. So one possibility is an extension or a strengthening of submodularity. So submodularity alone doesn't imply this. To understand this, the simplest way is to consider n equals 1, just a function in one variable defined on the integer point. So any function is submodular. Okay? If you consider p and q, two integers, minimum is one of them, and the maximum of the other. So any function in one variable satisfies submodular inequality. So it has nothing to do with convexity. That's why. So we need stronger condition. And that condition is this. Start with 2 points as before. And we say that P same and Q, G, P, and Q. Of course, I'm adding something. Yeah? So very close to submodularity. But I'm adding stronger condition, P minus alpha 1, where alpha is non-negative and integer, okay, for any. And this is Q, but here, and take this. So I added something. So for any alpha non-negative, this must be true. So if I fix alpha to be 0, then this is the original submodularity. But since it imposes this inequality for all alpha, is stronger than original submodular inequality. And I call this translation submodular. The translation is involved, so translation submodular. And it turns out this is equivalent to that. Okay? This is a good exercise, but the first try when n equals 2, then you will see what is happening. And then the formal proof is just by induction. Not very interesting. It's a good work, but not very interesting. So if we draw a picture, what happens in 2 dimensions? Well, maybe it's better to use that part. This is not really important. So maybe let me draw a picture about this. Actually, I explained this, that this should be true for all alpha. But alpha 0 is important for submodularity. And also, to understand what it means is we can consider P is bigger than Q. What happens in this case? In that case, P is here, Q is here, and P is somewhere here. And now alpha is small number, first 1 or 2. Then this vector goes this way. And this vector goes this way. Okay? And since Q is here, so we still have this point. So this operation doesn't mean anything. So that means if we come closer, the function value should not decrease. So this is the essential property of convexity. So if we have convex function at 2 points, and 2 points come closer in some sense, of course, in that case, on the line segment connecting these points. But here, we have only integer points, so we cannot really connect 2 integer points. Then we might have no integer point on the line. So we are imitating that. So this operation keeps us on the integer lattice. Okay. But still, if you see this picture, these 2 points are closer. And the function value should not increase. So this captures some convexity property. Okay? And if alpha is larger, say like this, then it doesn't make much sense to talk about the values outside this box. It is too much. But here we have some operation. So truncating this to this. Okay? And this operation truncating this to this. Actually, this part corresponds to this. So we remain in the box because of these operations. Okay? So that is the essence of this inequality. Okay? So in addition to submodularity, we have kind of convexity here. So implemented it as inequality. Okay? Now, this is equivalent to the following. The next thing is something like this. So imagine you have a convex function, P and Q, and you consider midpoint. Then the function value should be smaller on average, I mean. And if you want to imitate this, if you have, say, two variables, P and Q, then the middle point is here. And we compute the function value at the middle point. But the problem here, again, the discreteness. Even if P and Q are integer vectors, the middle point may not be. So we would like to approximate this midpoint by neighboring integer points. Okay. So this is the content of the next inequality. So if we start with, again, the value at P and Q, and it should decrease or remain the same at the middle point. But middle point is now replaced by, this is the middle point, but now replaced by rounding up all the components at the same time, and also rounding down all the components at the same time. Okay? For any PQ integer vectors. And this is, so we jump into the middle. Here we say close together slowly, but here we jumped into the middle. And the point here is we simultaneously rounding up all the components. We could have approximated this point by this, but we usually, but actually we use these 2 points. And this is equivalent, and sometimes very convenient. Now, in the special case, let's consider P and Q to be 0, 1 vectors. Special case. P, Q, both 0, 1 vectors. What happens? Then P corresponds to some set. That means that if an element is contained in that set, then Pi is 1, the characteristic vector. So this is a character vector of A, and this is characteristic vector of B. What it says? Good. So this operation, midpoint rounding up, is characteristic vector of union. Okay, 0, 1 vector, and this is equal to 1 if one of them is 1. And similarly, now you see that rounding down is intersection. So in this particular case, this is submodular set inequality. So submodular set function satisfies this inequality, actually. So in this sense, L-convex function is pretty much related to submodular set function. Okay. Maybe I have to hurry up. Okay. So, but yet another one is this. Now suppose, I'm giving a different characterization. Suppose we have 2 vectors. Then, say, P minus Q can be drawn in this way. These are components I, 1 to n. So suppose we have a sorted case. This is P and this is Q. And suppose that Pi is Qi for some I. Okay, so at some point, at some coordinate, P is bigger than Q, this assumption. Then call A to be the set of index I such that this is max of Pi minus Qi. I here. So that in this picture, A is this set. Okay. And then, so this exists. I mean, under this concept, under this assumption, we want to decrease this and increase this. So GP plus GQ is now P. So we come closer by changing this part. Minus EA. This is 1 on A and 0 otherwise. Plus GQ plus EA. This is a local sort of the directional derivative, and it also shows some convexity. And these characterizations are useful in different ways. But okay, so it's a good exercise to show that these are equivalent. Okay? Nothing is difficult. Okay. Okay, so I have defined L-convex functions and natural convex functions, and I have shown the canonical example. And in the program set, this is maximum. So you take the component vector and you take the maximum component truncated by 0. So by any number. So this is L natural convex function. Okay. Or G is a difference of maximum P1 to Pn minus minimum P1 through Pn. The maximum minus minimum. This is L-convex function. So if you increase uniformly the component, then they cancel. So we have the second condition easily. The point is submodularity. But once you have shown this is L natural convex, then this is a similar. Okay, so maybe I have to hurry up. So the second part is optimality criterion. So convex function has a minimum if it is locally minimum, okay? And similar thing is true for L-convex function. So if G is L natural convex, then we want to know that P in N is minimum. If and only if some local optimality is true. Okay? So remember that in this one-dimensional case, this point was optimal if and only if it is smaller than or equal to the neighbors. So in this case, we have to define neighbors. And here is a neighbor. So P is here. These points are neighbors. So if and only if the function value is bounded by P plus EA. So it just increase by 0, 1 vector for any A. And also you should decrease by 0, 1 vector. Okay. And what is good here is that we can efficiently check this condition. The reason is that, so consider this part. This is the same as saying that G, this function, the difference, let's call rho, takes a minimum at empty set. And rho is a set function, but because of this is a function in A. Because of this is a submodular set function. So the condition here is a submodular set function defined in this way has the minimum value 0. And we can use submodular function minimization algorithm to verify this condition. Okay? So efficiently we can solve this problem. And similarly for this. Okay? So this is local optimality condition for L. And using this fact, we can design the descent type algorithm. Here I said that we can verify the optimality. But if it's not optimal, then we can find A, which decreases the function value. So we can proceed the descent method. And of course, we have some choice, so we can introduce some idea to bound the numbers. Okay, that is L. Now, but still, I have to tell you something about convex extension, which I announced already. Why this function, L or L natural convex functions, can be extended to ordinary convex functions. Yep. So so G is defined on an integer point. So these are points we know. And here, I'd like to construct some function which is convex in the ordinary sense. This is L natural convex, or L-convex, say. It's easier. Such that this coincides with a given function on integer points. How can we do that? Now, as I told you that in each hypercube, G is a submodular function. Okay? And if you learn something about some modular function theory, the convex extension can be constructed in a concrete way. It's called the Lobos extension. So in the two-dimensional case, you divide the square consistently in this direction. Okay? And in each square and in each triangle, you construct a linear extension, which is uniquely determined because of this simplex. And what we already know is that in this unit hypercube or square, the extended function is convex if the given function is submodular. Okay? So we already know that this is convex here in each, but still we don't know what happened with this line boundary. But now we are talking about L-convex function, which is simpler than L-natural convex. L-convex function is somehow invariant, moving towards this direction. So if you are worrying about convexity at the boundary points somewhere here, so you could just move this point inside here because of the invariance. Then here around, this is convex function. So here we must have convexity. And maybe you are worrying about this function at this point. This is much more complicated, but if you move towards this, you are still on the boundary of simplex, but your interior in the unit hypercube. So that's why we can claim that the function is convex in this neighborhood because of Lobos extension. Then we can prove back to this point to show that this is convex. So this is how the convex extension of L can be constructed. It's simple, but it's just built on the Lobos extension. And now you will see how important it is to have a uniform, say, invariance in this direction. Okay, so that's it. Now, any questions about L-convex functions? Any comment or questions? Or?
So for L sharp is harder to do.
Sorry? So, but it's not sharp, it's just natural. So sorry for that notation.
L natural, you also have a convex extension.
Oh, yes, yes. Also, L and L natural are essentially the same. But to use a logical translation, it was easier for me to work on L convexity. That's why I have chosen L convex here. So L natural convex function, of course, is convex extensible. Any questions? Okay, then I go on to M. Actually, M convex function seems more difficult intuitively. But oh, now I see it's better to erase now so that I don't have to worry later. Okay, so M-convex function is a generalization of matroid. So yesterday I mentioned exchange property of matroid. If you have two bases, you can exchange element. And I'm now doing similar thing for functions. Okay, so f is again defined on integer point, and we consider the following exchange axiom, or I call exchange axiom. That means I use this property as a definition. Okay, f is M-convex if it satisfies this exchange axiom. So take two vectors, x and y. X and y. Okay, like basis, and take any I such that xi is larger. So in this picture, I is here. Xi is larger than y. Then there exists, you can find j such that xj is smaller. In this picture, j is in this direction. And the function value, fx plus fy, this original sum, is not smaller than the new point. Okay, and close to x. So here, so we are coming closer. So I is here. So in convex analysis, we move on the line segment. But as I told you before, we have to work on integer points. So we go this way. So that means EI plus EJ, EI minus EJ. Okay? So we compute the function value at this point. The condition says that again, start with any point, x and y, and take any I, if such I exists. If such I doesn't exist, you are done already at this point. For any such I, there exists some j with opposite direction in the sign, such that exchange I and j, the function value, sum of the function value, does not decrease, does not increase. Okay? That means, good question. That means, so Jens asked me, what if we have x here, y here? So then we cannot be able to find such j. The trick is that in that case, everything is plus infinity. Okay? So to be precise, I have to say that for any xy in the domain, that means that for any fx and fy, both finite, then that must be true. That implies that if we have such a situation, we are in trouble. This should not happen. So this implies, actually, a domain of definition f. This means the set of x's at which f is finite. Okay? Domain f is set of x, fx is finite, okay, is contained in some hyperplane defined by this inequality for some integer. Sorry?
R will be the rank of
Oh, yes. So in the case of matroid, this corresponds bases. So all bases must have the same cardinality. And that means that the sum of the components, in the case 0, 1, have to be equal to the rank of the matroid. And with that convention, so this implies that this should be true. So you should not draw such picture. Okay? But this is actually at the beginning, it's a good question. People are often confused with this situation. Okay, this is the definition of M-convexity. But as we already see that M-convex function defined always on this line. So we have extra dimension. We could have projected. Yes?
Yeah, so if we had a matrix,
Matrix, yeah.
R is the rank of the matrix.
Yes.
And what will be f of x? Will be if it's a base or not?
Okay, okay, yes. In that case, okay, maybe I could give you the it's an indicator function of the basis family. Okay, so I will write. Yeah. So the example, as an example, is matroid, say, E and B. Let's say matroid. And B is the family of subsets. So that means we can identify B as a subset of zero vectors. Is okay? So this is, of course, subset of the N. And we are going to define a function f to be 0 or infinity according Lx is in beta or not, B or not. Okay. So then this axiom says that if we have finite fx and finite y, that means if we have two bases corresponding to x and y. Okay. If we have x and y and base, that means f of ex and f of ey are both 0. Okay? Now let's look at that axiom. And then the axiom says for any x, or not x, I in x minus y, that means xi is 1, yi is 0. Then there exists some j because of this. Then we exchange I and j. So that means exi plus j and f e y plus I minus j equal to 0. Okay? Because we started with 0 on the left side, we must have 0 on the right. Otherwise, we cannot have plus infinity on the right. So this must be true. So this means that x minus I plus j is in the base, and y plus I minus j is in the base. So yesterday I mentioned 3 kinds of exchange axioms, and this is the third form, simultaneous exchange. Okay? So this is how matroid is related to this concept. Okay, thank you. It's okay? Now I'm going to define M natural convex function. Okay, so M convex function is defined on this hyperplane. Okay, F is actually defined on this, and plus infinity otherwise. So why don't you project? So suppose this is M convex and plus n plus 1 variables. Then we define f of x by f the variable for x tilde denoted as this, starting with 0. Then no. 0 and 4. Okay. If the here it was plus infinity, so but on this here, if they are on this hyperplane, we take the values. X is x1 to xn. Bit strange. Okay.
Don't need the second case. Don't need the second plus infinity case.
Plus infinity case is not otherwise but x1 through x0, 0 to xn is not equal to on.
So there's no x0, 0, right?
Then
Right.
yes, you're right. I'm confused. Oh well. No, this is okay. Simply this, yeah. So if function f is derived from M convex function in n plus 1 variable in this way, then this is called M natural convex function. Oh, I've only found 5 minutes. Okay, yeah, I can continue the next. Now, since M convex function was defined in terms of exchange axiom, maybe we can translate that exchange axiom for M natural convexity. Okay? So exchange axiom for actually proposition is this: F is M natural convex if and only if it satisfies the following exchange axioms. Very similar to that. For any x and y and the domain, I now use the domain here. And for any I such that xi is bigger than y, the same up until here, then either this is true if x minus ei. So the first case is that you do not need to exchange. You simply come closer by this element. Or there exists J, the same statement as before. Such that we have the same inequality of exchange type. Okay, so this is a convenient exchange axiom. And now you know independent set of matroid. So for independent set, the family of independent set, say I, you can define this function. Then that function satisfies this. And the first case, suppose we have x and y. And if you have I here, then x minus ei is obviously independent set because of the hereditarity. So this is 0. But here, depending on the I, could be plus infinity. But this axiom said we have to be able to find I. Well, no. If you cannot add I to y, then you have to be able to find j somewhere. And we can exchange. But we have to have this condition. So in such a case, this cannot occur. So if we have this, since x is independent, always we can add I. So this is a trivial case. What do we have to? So this is what I wanted to say. Okay. If you cannot add to y, then you have to be able to exchange with some element j. This is what is said by this condition. Okay. So this M natural version corresponds to independent set, and M corresponds to basis. And they are interchangeably equivalent, just as in matroid. Okay, so finally, maybe I should give some example. And I will stop at this point. So I mentioned that separable convex function is in the intersection of L natural and M natural convex function. And for separable convex function, the exchange property is almost trivial. You can think of that. And the less trivial, more important class is what is called laminar convex function. So I will explain that and here and leave the proof to the exercise. It is included in exercise. So the statement is the following. So suppose we have set E and family of subset F. So we have E here, and we have bunch of members, F. And F is called laminar. F, it's called laminar. If there's no intersection. So for any A and B in the member, A is containing B, A is contained in B, or A and B are disjoint. Okay, so it looks like this. And this often happens in connection with tree structure. If you have a tree structure actually equivalent, if you have such a family, you can represent this in the tree structure, and conversely. And now, suppose we have this family, and suppose we have a univariate convex function for each A in this family. Now I say that following construction, f of x is an eigenvector, summation of all members in this family, and for each member we have the convex function, but argument here is the sum of the component in A. And so each of this is a convex function, okay, in the ordinary sense. And so the sum of the convex function is a convex function, probably. The claim is that F laminar implies F M natural convex. So this construction is very convenient. And actually, there's, of course, there is an M natural convex function which is not in this form. But in applications, quite often, M natural convex function arise in this way. And in the exercise, I have given somehow this is true. Somehow. In the sense that we have no, say, degenerate situation if these functions are independent. If such a function is M natural convex for some family, then the family must be laminar. Okay? Of course, we have to formulate what the non-degeneracy means, but say if you find the function randomly, and if you happen to be M natural convex, then your family must be laminar. Okay, so maybe I should stop here, and I continue M natural convex function on Thursday. Tomorrow I will have no lecture. Thank you.